start watch for the ROS2 topic list. And we can see that we don't have any topics here now. And I can start one robot node. And we can call or provide the ROS2 service call to the robot logic start service, and this application takes one argument, and it's the base name of the machine learning service. So the communication service between the communication machine learning control service will be presented under the node machine learning control services. So this is the only thing which needs to be specified when we are starting processing from the robot. When I start the processing, you see that robot starts sending the data. The generated topics appears, and the robot is showing us the processed video files and the result of the detection, and he prints out the data from the result. So we have here some header. Yes, okay, I will call them stop service to stop the processing. And when I call the stop service, you can see from the robot node that the robot sends or communicate over the stop service of 5G-ERA machine learning control service request, and that the machine learning service server respond that he killed the nodes, and robot will destroy the publisher and the subscriber to the topics, and the same will be done even in the machine learning service center controls server. So you can see that the topics disappeared here. And we can even start two different robots. So I will start the one robot here, and we will start another robot. In this case, we need to define the name for the second robot to be able to send the start service and stop service calls to this robot node. So I will start even the second robot, and we can check the ROS2 node list. And you can see that we have two nodes running. So this is the first robot and this is the second robot. And I will start watching the topic list again. And first of all, I will call the start service again for the robot logic node. So the processing of the first robot starts, and I can run the start service request even for the second node. Data are being processed, and this is the result for the second robot, and these are the detections for the first robot. When I call the stop service, the first robot will end and the topic will disappear, and it's the same even for the second running robot. You can see that I left here the argument of the machine learning control service, but it's not necessary. If I start the second robot again, and I can stop it even without this this argument. So this is the basic communication which has to be implemented between the robot and the machine learning service. So the robot can ask for registering of data processing, gets the topics, and start sending data and obtaining the results. So I will clear our environment now. And we can move to the last, maybe most complicated part, but before we do that, I will delete the deployment of this configuration. You can see that it's terminating, so it's okay. Last part is focused on the distributed machine learning service inside the Kubernetes cluster. And this service is composed from multiple parts which are deployed in the Kubernetes individually. And the previous standalone version is broken down into 4 different parts. First part is the ROS2 control service server, which is the machine learning interface. And this is the part which provides us the registration of the robots and processing of robot messages and sending back results of the detection back to the robot. So you can see that this part between the robots and the machine learning interface uses the ROS2 communication, and from the machine learning interface we have communication over the celery, or using the celery over the RabbitMQ, which is the advanced messaging queuing protocol. And the RabbitMQ here in our implementation is used as task broker. So we use the Celery, which is the system for distributing tasks to the running workers. And the tasks are distributed over this RabbitMQ. We have multiple workers. It can be one or more instances of the machine learning service itself. In our case, it's the object detection, which is serving the tasks. So if we have a request for if the machine learning interface will get some image message from the robot, it will process the data and sends and begins and creates a task over the RabbitMQ, and some of the running worker will take this task, completes its function, and store the results back to the Redis in our case, which is used as the result storage. And so the Redis here in this example is the Celery backend for storing the results, and the machine learning interface can see to the Redis, and it can read the data from the Redis after they are finished, and the result of this task is sent back to the robot using the ROS2 communication over the publisher-subscriber type of communication. So if we take a closer look to the deploy and test part, this is something which is running, which is here presented in more like high-level concept, but for us it's all the same. We have still the robot with some control service client. We have the service, and we have the control service server running, which is creating the new nodes with dedicated publisher and subscriber. But in this case, this subscriber node is connected the subscriber node implements the Celery asynchronous task call. So if the subscriber gets the image message, it will convert the data and use the Celery to send data to the Rabbit, and the node will store the task ID, which is obtained from the Rabbit, and with using this task ID, it asks Redis if the results are already processed or not. So in the host system, we are running only the robot, and in the Kubernetes cluster, we are running more pods. The first is only the machine learning service interface. The second one is the broker. Another one is the result backend, in this case Redis, and we can have multiple replicas of machine learning service workers. Now we have to take a look to the 5G-ERA machine learning service distributed configuration of the Kubernetes cluster, which will be deployed now. And in this case, we can see that